In chapter 6.2, we look at a new concept called electronegativity and polarity. Before we look at the actual definition of electronegativity, we are just going to look at a covalent bond. So I'm going to draw two chlorine atoms with a bond between them, and we know that a covalent bond represents a shared pair of electrons. So I've drawn a pair of electrons evenly shared between the two chlorine atoms. Shared pair of electrons. And up until now, we have always assumed that those electrons are evenly shared between the two chlorine atoms. But in some cases, the electrons in the covalent bond are not evenly shared. So for example, if I were to draw a hydrogen-oxygen covalent bond, instead of those two electrons sitting in the middle, equally shared between hydrogen and oxygen, those two electrons are actually going to sit closer to oxygen. If I were to draw another bond, this time between oxygen and fluorine, okay, the pair of electrons in the covalent bond between oxygen and fluorine, in this case, actually sit closer to fluorine. And we call this ability of an atom to attract a pair of electrons, we call this electronegativity. So the definition for electronegativity is the ability of an atom to attract the bonding electrons in a covalent bond. And atoms that are really good at attracting a pair of electrons, we say that they are electronegative. In the first bond that I've drawn, both atoms are the same, so neither chlorine atom has an advantage over the other, and neither has a stronger pull on the pair of electrons. In the next bond, you've got hydrogen and oxygen. In this case, hydrogen has a stronger pull on those electrons than hydrogen, so the electrons sit closer to oxygen. In the next bond, we've got oxygen and fluorine, and in this case, fluorine has a stronger pull on the electrons than oxygen, and the electrons sit closer to fluorine. So what is it that makes an atom electronegative? Why does oxygen have a greater pull than hydrogen, but fluorine have a greater pull than oxygen? Why is fluorine more electronegative than oxygen? Okay, to look at this, we need to consider what a shared pair of electrons actually is. Okay, we know that electrons have a negative charge. Okay, so those pair of electrons are negatively charged. And if we think back to our definition of what a covalent bond is, we saw that the negatively charged electrons in that pair of electrons, they were attracted to the nuclei of both bonding atoms. Why is a pair of electrons attracted to the nucleus? Okay, what's in the nucleus? In the nucleus, we have got protons and we have got neutrons. Neutrons have no charge, they are neutral, but protons have a positive charge. Okay, so you've got your negative electrons in the bond, they are attracted to the positive nucleus. Okay, we say the amount of charge that an atom has in the nucleus is its nuclear charge, and the nuclear charge in an atom is determined by the amount of protons it has. So if we compare hydrogen and oxygen, I'm just going to draw this bond underneath again. We compare hydrogen and oxygen, and we said the electrons are sitting closer to oxygen, okay? Hydrogen has only got one proton, which means it's got a nuclear charge of just +1. Oxygen, on the other hand, has an atomic number of 8, which tells me it's got 8 protons, and it's got a nuclear charge of +8. Because oxygen has a greater positive charge in its nucleus, oxygen is going to have a stronger pull on those electrons than hydrogen, and the electrons will sit closer to oxygen. We can say oxygen is more electronegative. Underneath, if we compare oxygen and fluorine, okay, fluorine has an atomic number of 9. It's got 9 protons. It's got a nuclear charge of +9. Oxygen, as we've just seen, has 8 protons and a nuclear charge of +8. Fluorine's got a greater nuclear charge. The electrons are more attracted to fluorine and will sit closer to fluorine than they will to oxygen. How about if we consider, though, I'm going to compare oxygen and sulfur. Okay, so if I look at the number of protons that they both have, sulfur has 16 protons. It's got an atomic number of 16. So it's got a plus 16 charge in its nucleus. Remember, neutrons are not charged, they are not contributing. And we've seen that oxygen has a plus 8 charge in the nucleus. So based on what we've seen before, you would expect sulfur, with double the amount of positive charge than oxygen, that sulfur is going to be more electronegative and sulfur is going to have a greater pull on those electrons. But in actual fact, it's oxygen that has a greater pull on the electrons, okay? So it's not just about the amount of protons that you've got. There is another factor that you have to consider, and that factor is size. If we look at our periodic tables, we see that oxygen is here in period 2, but sulfur is down here in period 3. Sulfur is a much bigger element. And what that means, if I go back to just drawing my old school GCSE electron shell diagrams, so this is my nucleus for oxygen, is that sulfur, because it's in period 3, it's a much bigger atom. And sulfur is forming a bond with its electrons that are out here in the third shell, while oxygen is forming a bond with the electrons that are out here in the second shell. Sulfur's bonding electrons, the electrons in its outer shell, are much further from the nucleus than the bonding electrons in oxygen. So even though sulfur has got a greater nuclear charge because it's got more protons in there, because sulfur is so much bigger than oxygen, the bonding electrons are further from the nucleus, and that nuclear charge is cancelled out by the increased shielding or the increased number of electron shells. So when you're looking at electronegativity, you're not just looking at how many protons something has, you also have to consider the size of the atom. For something to be really electronegative, you want something that has a high nuclear charge, so lots of protons in there, but you still want it to be small. And there is a table that compares the different elements together, and it shows you the different values of electronegativity. And on this table, you can see that fluorine has the highest electronegativity value. And we call these values Pauling values after the scientists who discovered them. And fluorine is given a Pauling value of 4, which is the highest on the periodic table. The reason that fluorine has got such a high value is because it's in period 2, so it's small and its bonding electrons are close to the nucleus. And of the period 2 elements, fluorine has the highest nuclear charge. It's got the most protons of the period 2 elements. So fluorine is your most electronegative element. You can see that oxygen also has a high value of 3.5 for, again, the same reason. It's got 8 protons and it's in period 2. You've got nitrogen's electronegative with a value of 3. And you've also got chlorine down here, which is still quite electronegative, okay? Yes, it's in period 3, so period 3, so it's a bigger atom, but it's got 17 electrons. So with 17 electrons, it does still have a pull over the electrons in a covalent bond, okay? So just be aware that in bonds that have 2 different atoms, like what we've seen before, those electrons are typically not going to be evenly shared. One atom will have a greater pull on the electrons than the other atom. And we call these bonds, okay, I'm going to draw this down here. We call these bonds, where the electrons sit closer to one atom than the other, okay, we call these bonds polar bonds, okay, so they are polar covalent bonds. And because oxygen has a greater pull on the electrons than hydrogen, we can also assign charges. Now, we've seen when you had ionic bonding that if a metal loses an electron, it becomes positively charged. Now, hydrogen is not actually losing its electron, okay? It's still in the bond between hydrogen and oxygen. Hydrogen hasn't fully lost the electron. But because hydrogen's electron, which is what I've represented here with the cross, is sitting so much closer to oxygen than it is to hydrogen, we can assign hydrogen a delta positive charge, okay? Positive because it's lost an electron, but delta positive because it hasn't fully lost the electron. The delta is telling you that that charge is small. It's not as big a charge as a normal +1 charge where it's properly lost an electron. Okay, it hasn't properly lost the electron, so we're only saying it's delta positive or partially positive. Similarly with oxygen, we can say that it is delta negative or partially negative. It hasn't actually gained hydrogen's electron, but because that electron is sitting so much closer to oxygen, we can say that it is delta negative or partially negative. If you had two atoms that were the same, like we did above with chlorine, and those electrons are evenly shared, okay, neither atom has a greater pull on the electrons, so neither atom becomes delta positive and delta negative. We say that this is a non-polar bond. And between two, a covalent bond between two of the same atoms is always going to be non-polar. In some cases as well, like in the case of carbon and hydrogen have very similar electronegativity values, and even though both atoms are different, we say that it is a non-polar bond. So to see if something's polar or non-polar, don't just assume if the atoms are different that the bond is going to be polar. Look at the Pauling values, see what the difference is. If there's not that much of a difference between the two, we're going to say it's non-polar. And if there is a great difference between the two, then we're going to say that it is a polar bond, okay? In polar bonds, as I've mentioned, you get this separation of charge. One end of the bond becomes negative, the other end of the bond becomes positive. And because you've got this separation of charge, we say we have a dipole, okay? A dipole is just the separation of charge across a covalent bond. In exercise 1 on page 15, I've just given you a list of covalent bonds. I just want you to tell me if they're polar or non-polar, and if they are polar, to assign delta positive and delta negative. To see which one is going to be delta positive and delta negative, you'll have to flick back up to page 14 and use the values on the table. Okay, so have a go at that, pause the video, and then come back for the answers. Okay, I've done the answers to exercise 1 here. Okay, so hydrogen, bromine, that is a polar bond. Bromine is more electronegative, so it's going to be delta negative. Hydrogen will be delta positive. Bromine, two of the same atoms, it's a non-polar bond. Nitrogen, hydrogen, nitrogen's more electronegative. It has a greater pull on the electrons, so nitrogen will be delta negative, hydrogen's delta positive. Between fluorine and chlorine is an electronegative element, but fluorine is more electronegative. Fluorine is the most electronegative element. So in this bond, fluorine is going to have a greater pull on those electrons. Fluorine will be delta negative, chlorine will be delta positive. Over here, we've seen this one already. Polar bond, oxygen's delta negative, hydrogen's delta positive. Carbon, hydrogen, there is a difference in their electronegativity values if you look at the Pauling table, but that difference is small, and we say that it's a non-polar bond, and you're going to see that a lot in the chapters to come, that we say that carbon-hydrogen bonds are non-polar. And at the end, you got oxygen bonded to fluorine. Remember, fluorine is the most electronegative atom, so even though it's bonded to another electronegative atom like oxygen, it will still have the greater share of the electrons. Fluorine will be delta negative, and oxygen in this case will be delta positive. The only time you're going to see a delta positive in oxygen is when it is bonded to fluorine, okay? In the next video, I'm going to look at molecules and how to work out if a molecule overall is polar.